Hello, everybody. This is Professor Ma, and this is the L'Hopital's rule part two. Talks about the exponential ambiguous form. So we have this exponential. First, we're going to phrase in this case as n goes to infinity, and so in 1 over n goes to 0. So this is what we mean by usually, of course, think about in the head when we look at some power goes to 0. We're taking roots basically. Okay, so we have this ambiguous form, and in particular. Yeah, the first one, look at what happened. If I look at this is simplified to 1 over n. So in particular, let me get a pen out. That's here. So this is one half, 1/3, and so on, so on. So the limit of this is 1 over n, and goes to 0. But on the other hand, if I look at the following limit of 1 over n to the 0 power, then it goes to 1. So therefore, if I plug in and the base goes to 0, the power goes to 0, I really cannot tell which case it is. So it's ambiguous. Yeah. Similarly, we have infinity to the 0 power. Okay. And so in this case, the base goes to infinity as n goes to infinity, and the power goes to 0. But really, this is just n, and so this goes to infinity. But on the other hand, we will see later on the bottom one. If I take the nth root of numbers, it goes to 1. Okay. In particular, to take a look at this one, we're going to observe one basic. Take any positive number. You take any roots, keep taking the roots, then the limit goes to 1. For instance, if I start out with a quarter, and then the root of a quarter, square root of a quarter is a half, somewhere over here. And the third root, it goes up. Same thing on the other side. If you keep taking roots, it gets smaller, squeeze toward the number 1. Okay. And the questions we have, okay, in this case, is what happens if the base gets big and the bottom gets close to 0. Okay. So what happens if I play around with the base? Okay, let it go to 0 a lot faster, let it go to infinity a lot faster than as changing simultaneously. What happened to taking roots? So we call these type of problems we say this the form of exponential ambiguous case. Okay. And how do we deal with this? Well, the one technique, take the log of the things, and we're going to use a basic fact. And suppose I want to find out the limit of some formulas. X approach something, X approach base, okay? And I want to know what the limit is. And so what I do instead, we write this as e to the log of that formulas. And so we pass the problems of finding the limit to this. I suppose I find the limit of the log is 5, then my original question has an answer. It's going to be e and replace the exponents of the 5. Okay, so whatever I find the answer for the log, all I have to do is just put that answer back as exponents, and that's the limit of the original formula. In other words, okay, this ambiguous form. So we take the log of it, and now we investigate what happened as x goes to infinity. This is where L'Hopital's rule comes in. A lot of times, log form will come out to be a fractions that we can use L'Hopital rules from last sections. Take the derivative of the top and derivative of the bottom. Okay, so L'Hopital's rule. Now plug in infinity. The limit goes to 0. Remember, this is the exponents we found. The log, this is the limit of the log of the original. So put this back on top of E, and so we get the limit of the original problem. Okay, and this trick works for x go to 0. If x is shrinking, and this is basically what we just said, taking roots, it goes to 1. And we can verify these by using the log of the formulas. Okay, and I log it, the exponent comes down. Okay, and then this is actually, it can be converted into a fractions. In terms, I can use L'Hopital's rule because now it is a infinity over infinity rule. Okay, L'Hopital rules, I can take the derivative of top, derivative of bottoms, and these simplify to minus x, and x goes to 0, then this goes to 0. So the original limit of this goes to e to the 0 or 1. Okay, same trick. This is the questions of 1 to infinity. Suppose I take the number, a number that's very close to 1, raised to a large power, state somewhat close to 1. So here is a situation where the exponent goes to infinity, but this is shrinking to 1 at the same time very fast. But same time, you are multiplying out because of the exponent become bigger and bigger. And so where will this stabilize? And okay, and this is 1 to infinity power problem, ambiguous case. Log it. Okay, so we're going to investigate the log. Oops, control-V. The log of these, and of course, the exponents comes down, right? And log of fraction, let me break into 2 pieces. Log of x plus c minus log of x. So I'm going to, okay. So I'm going to use L'Hopital's rules. Okay, I put the x underneath and flip into fractions, and write the top as difference of 2 log. Okay, what? Because now I can use L'Hopital's rules and take the derivative of tops and derivative bottom. Okay. Continue. This is just a fractional calculation from here. Okay, so in this algebra is a little exercise in calculating fractional, linear fraction, simple fractional terms like these. And then you will find out everything cancels. Okay, and so I let yourself clarify with this algebra, and what you wind up with is C. Okay, going to use L'Hopital's rule again. Okay, so this algebra will be on the test. Okay, so in other words, put the C back in exponents. So limit of these expressions is e to the c. In particular, very important, if c is 1, I get the value e. So in other words, as x goes to infinity, this goes to e. Okay. Or if you put integers, 1 plus 1 over n raised to the nth power, as n goes to infinity, this goes to e. If I just use the positive number. That ambiguous form of subtractions, well, put them into a fraction. So we can use L'Hopital's rule, okay? In this case, if I let x go to 0, the front part is infinity. The back part is infinity. It just means you're going to have two numbers, a large number subtract a large number, but the who comes out ahead, is there a limit that is to be decided, and how do we decide that? Put them into a fractions, okay? So we can employ L'Hopital's rules. Okay, and here if I put into a common denominators, then take the derivative of the top, take the derivative of the bottoms, and the bottoms I use the product rule. Okay, the tops is easy, right? It's 2 term cosine x minus 1. Now put in 0. Okay. Well, I still get 0 over 0, so I L'Hopital's rule again. And derivative cosine now is minus sine, and derivative sine is cosine, and then use the product rule again. Okay. That finally I get the following limits. If you put in 0, you get this to be 1. This is 1. Okay, this can be gone, and so 2 in the denominator, and the top of course is 0. So this is how we deal with infinity minus infinity. Okay, that's it. So this is a bit the ambiguous form for exponential type of functions. Okay, bye-bye.